Hello, everybody.
Hello. Hi.
Let's see. Excuse me, just took a cough drop. I wanted to show you just, this is nothing that's on the test, but just some interesting things about data in that little survey that we had. And I surveyed my wife and kids too, just to add some numbers to it. And let's see, so I have the results of that. And there were only two choices. And so something else that would have two outcomes would be flipping a coin. So let me find it here. A coin flip simulator. Like you really need a simulator for something like that, right? Sorry if there's ads and stuff on this. Let's see, I think it's going to, I don't know about all the drama here. Okay, here's where it counts. I played around with it a little bit. I thought I figured it out, but I don't need global stats. I just need my stats. Oh, my stats right there. Tiny little thing. Okay, I'm going to flip it, I don't know, maybe 20 times. And what do you expect? You flip a coin 20 times. About how many heads do you expect to get?
10.
10, yeah. And that's an example of classical probability. If there's two outcomes, then we expect them to be equally likely. And now, of course, when you flip it a small number of times, you may not get exactly 50%. But the more you flip it, there's something called the law of large numbers. The more you flip it, the closer it gets to 50%. But every flip individually has a 50-50 probability, heads and tails. I haven't been paying attention. What are we up to? 11 flips. I can stop there because I have 13 results for the fruit. Heads and 7 tails out of 13 flips. So pretty much, I think what we expected. So for the coin, I had 13 flips. I got, oops. What was it? 7 heads and 6 tails.
It was the opposite, but I don't really think it matters.
No, it doesn't matter. Might as well do it right if I'm going to do it. So 6 heads, 7 tails. Thank you. And then for the fruit survey, the pear was preferred by 2 people, and the strawberry was preferred by 11 people. So not a lot of love for pairs out there. Now, this one came out about like we expected, really close to 50-50. What happened here?
I guess it was more of an opinion, so it's different. Is that like what you're asking? Like, what's like the difference between them?
Yeah, and I think that's exactly what it is. These are flipping a coin is called a random event. There's no influence on whether it's heads or tails. You just flip it, so you expect them to be 50-50. When you ask people something, people are not random events. What you like and prefer are likely very different than what I like and prefer. You know, if I asked about music, just the difference in our ages would probably mean that we have very different tastes in music. These are random events. So you have to be very careful, and I see it a lot in the media. When I say media, just in things I read, I don't watch a lot of TV. Where they break things down. Now I don't want to I don't want to stoke any political stuff, but so I'm just telling you what they say. You know, women, I think, comprise just about 50% of the population in this country, because birth is a random event. So we end up getting 50%. Yet, and I think they actually comprise a little more than 50% of the voting population in this country. Yet there's nowhere near 50% women in the Senate. Now, so you ask why it is, and often told it's some ominous influence out there. But truth be told, if women wanted to fill the Senate with women, they could certainly do it. They could certainly do it. I think they vote in higher percentages too. So if women, if gender was the most important thing for them when they vote, then they could certainly fill the Senate up with women, probably more than half women. Yet there's not any. Well, that's because they have different preferences and different desires. Now, I'm not trying to say what those desires are, but they do. So they don't land. It's not as simple. The women are not random events. They don't vote like we think they should. You know, we don't. You know, we don't force them to vote for female candidates just because they happen to be female themselves. So they have different wants and desires. Maybe they run for office in lower numbers for whatever reason. It's no fun running for office. I guess men are more prone to do it. I don't admire politicians, so I'm not saying that that's a good thing. That might be motivated by greed or other things that women are just not as willing to do as men. But there's all these different things, all these preferences that are built in us individually that cause us to do things, and we're not just guided by our gender or our race or our orientation or anything like that. So I guess this is just a point of just beware when people start hollering about overrepresentation and underrepresentation. It's a deeper question than just that. It's do they, you know, now you have to look if they have the opportunity. In college admission for the longest time, African Americans did not have the opportunity. So that would hold down those numbers. That wasn't a matter of preference. That was a matter of, in most cases, a government intervention and not allowing them in the institutions. So that can happen. So I'm not saying anything in particular, just that you can't stop with that first layer. You can't stop. You need to look a little closer and say, what's causing this? These people want different things. they have different preference. They like different things. They like to do different things. Some people like to go on cruises. I've never been on a cruise, and I have no desire to go on a cruise. That doesn't mean I've been cheated in life. It's just a choice I made. So anyway, I just take a little time when you read those things and dig a little bit deeper and see and consider the fact that there may be something else there. It may be as simple as what's on the surface, but not always that simple. And then I want to go back to our practice questions. And here's our class practice. I saw somebody once point out sometimes the entertainment industry, as far as that kind of stuff goes, is a good one to look at, because the entertainment industry is as free market as you get. There's no quotas. There's no government interference. There's no that. People, the people in charge promote people that are going to make them money. An owner of a football team drafts players. They're going to help him win and make him the most money. And so it's really as free market as you can get. So it's interesting to look at. And the NFL, for example, is, I guess you could say, overrepresented by African Americans, but it's not overrepresented. Everybody has an equal chance. Hispanics, Asians, and whites, they could all pursue those goals as well. But they don't, for their own reasons. And African Americans do in higher numbers. And then so they make up a much larger portion. And so it's not being overrepresented at all. It's just when you allow people to do what they want to do without any kind of interference, they get to choose what they want to do. And that's a good example in the music industry and in sports industries. I think in baseball, Hispanics may be higher percentage than they are in the country, but I think it's cultural in a lot of countries, Hispanic countries, to play baseball. So that's what they embrace and that's what they do. So we shouldn't expect things to fall along these lines that are so simple. And so, like I said, it's always interesting to look at an industry that no one's tried to manipulate and no one's interfered with. And it's just people acting on their own self-interest. They're doing what they want to do. And the people in charge want to make money. So they're trying to make the most money. And they hire the best people that'll help them win and make the most money. And so that's how it falls. And so it shouldn't be surprising at all. It's just people being allowed to do what they want to do. But anyway.
I love all the facts that you give, the information.
Yeah, it's interesting. It's interesting because I don't like to hear people squawk. There's hasn't been a white Heisman Trophy winning running back in 30 years. So, and my response to that is, so what?
Yeah.
Exactly. So what? They don't choose to pursue that. Other people do. Other people are better at it. The Heisman Trophy goes to the best player, and the best player is better at. There's no interference in the voting. So I just people really seem to object to letting people do what they want to do. So anyway, this is, let's see, I can't remember how far we got here. Now I do have a doctor's appointment today. I think my wife's going to be home about at 1:00 to get me. So we might have to end. I'll wait till she comes through the door. We did that, Ace Our Heart. That was a good one. That was those were not mutually exclusive.
I think we stopped at question 4. We did question 3, and question 3 was 713.
Gotcha. All right. Now let me see 4.
What was number 2 again? The answer to number 2?
I think it was
413.
413.
Okay, thank you.
Uh-huh.
Mhm.
Now 4, we need to get to the multiplication rule before we can do that one. So we're going to skip a few of these on the way through and just do the ones up to and including the addition rule. And this little practice thing is kind of messed up. Well, not messed up, it's mixed up. All right, here's one we can do. Try that, a single-sided die. Now this is not don't make it harder than it is. Single-sided die is rolled. That's a 6-sided die. Excuse me, a single 6-sided die, it tells us that is rolled. Find the probability of rolling a number less than 3. When we say less than 3 on a die, what do we mean?
The numbers under 3. 1, 2, 3, right?
They have to be less than 3. So
Oh, sorry. Oh, less than 3. I'm sorry. So 1, 2.
right, 1 and 2. So we have the probability of a number rolling a die and getting a number less than 3 would be. Now, how many, this sample space of rolling a die are the numbers 1, 2, 3, 4, 5, 6. How many of those satisfy the condition less than 3?
2.
That's right, 1 and 2. So the numerator is 2. What is the denominator?
6.
And why is it 6? You're correct, but why is it 6?
Oh, sorry. It went out when you asked me. It's because that's the number of numbers in a die,
That's
or
right.
in a single 6-sided die.
Yeah, and then the nerd term for that is the sample space. That's
Yeah.
the number of outcomes in the sample space, but you're 100% correct. Now you can see that these answers are all decimals. So
Yeah.
what would the answer be?
The one that the mouse is already on, the 0.333.
There we go. Does everybody get that?
Yes.
Yes.
Find the probability of answering. Okay, that's the next class question. That's next class. Here we go. This is like empirical probability. Probability, if you're picking somebody at random, that their birthday is in July. Excuse me. Sorry.
I see it.
So what would our numerator be?
Would it be 1?
Well, where did that come from?
Oh, I was gonna say the month of July.
Right, but now all the months are not equal. They don't all have the same number of days in them.
Oh, yeah.
So when you're talking about birthdays, you probably have to individually count the number of birthdays someone could have in July.
Oh, okay. So would it be the 31 over 365?
So the number of outcomes that fit a birthday in July, there's 31 outcomes. There's 31 days in July. So there's 31 different birthdays you could have in July. Now, how many total birthdays in the sample space? How many birthdays are
365.
there? Yeah, in a year, 365. So probability of having a July birthday when somebody is selected at random is 31 over 365. Now that's assuming, that is assuming that birthdays fall randomly. And I'm not sure that that's completely true. I think some months there's more birthdays in some months than others. Because there's
Like September.
Yes, literally.
Everyone's birthday. Like, I don't know if you have Facebook, Mr. Ritchie, but like every day, I promise you on my page, it's like 7 people's birthday. Please excuse my dogs. I'm sorry.
Yeah. No, yeah, that's a good point. And there's probably reasons for that. If you count back 9 months from September, there may be some reason for that. I don't need to talk too much about that, but it's not, there's typically other things going on, it's not just complete randomness. So, and you kind of notice that stuff. That's a good point. You kind of notice that stuff when you have social media and you see all of a sudden this big bump in September. And you think, what's going on? And you count back. So that would be over Christmas break.
Yeah, like New Year.
Yeah, New Year's, and you can make theories up about that and think different things about that. So it's not complete. I don't think this is complete randomness, but for the sake of this question, that's what we're assuming.
Yeah. May too, honestly.
Yeah, May.
Everyone and almost everyone in my family is May.
Really?
I have a lot of like August birthdays in my family.
Huh?
Yeah. May, August, September, honestly, is
Yeah.
the most for everyone I know.
Yeah.
Sorry. It's
the
so
fun-
loud. My dogs are fighting over. They both have the same toy and they're fighting over one of them.
Of course. Of course. They're like children, aren't they?
Yes, they are.
One of them's got the toy and the other one wants it. So there you go.
Right.
We're not all that different from our pets. I don't think in a lot of ways.
Not at all.
So yeah, in my family of 5, 3 of us are born in April, and then 1 in May, and then the last one in October. So we're heavily weighted towards April and May and springtime. But anyway, let's look at the next question. Here we go. Sorry, I've just had this hacking cough forever now. Excuse me.
No worries.
Yeah. Any guesses on this one?
Would it be the? Oh wait.
Now these answers are reduced, so you'll have to figure it out.
Oh, they are. Oh, okay, then let me actually.
Excuse me. Well, let me give you a little hint. How many aces are in a deck of cards?
4.
So that's your numerator.
Yeah, I got it. It's the 1 over 13.
Yeah. So somebody said 4, and I think
I
you're
did,
right.
but
like-
I hadn't done any math yet.
Yeah. Well, you did it in you're doing math while we're talking. So that counts. There's 4. And then how many cards in a deck of cards?
There's 52.
There you go. And then when you reduce that, like you said, 1/13.
Well, yeah.
There you go. So the numerator is the number of outcomes that satisfy the conditions, which was an ace, 4 aces. And the denominator is a number of outcomes in the sample space. Very good. There's another one to try. How many cards in a deck satisfy the condition of being a red card?
There's 26. Sorry, my sister came in and started talking to me. So
Oh, that's
I
okay.
had to kick her out.
Does everybody get that the red cards in a deck are all the hearts and all the diamonds? So there's 26 of them. Then how many cards in a deck?
52.
All right. So that reduces to 1/2. Now you might be wondering, well, half of the deck is red and half of the deck is black. So couldn't I just say 1/2? In this problem, you certainly could. But it's not always that easy. One deck drawn from a standard deck of 52 cards. What's the probability of drawing a heart? How many hearts are there in a deck of cards?
13.
13?
Yes. So
If you don't know cards well, you can always just Google a poker deck of cards and get the image of all the cards and count them. You know, you don't have to memorize what a deck of cards looks like. So what were you getting ready to say? Somebody started to say something.
oh, if it was me, I don't know if I meant to.
Okay,
But yeah, it's 13.
13. And what's the denominator going to be?
52.
Yeah, whenever you're doing a card problem, that's pretty much always the denominator, isn't it? It seems like it. And that reduces to what, 1/4?
Yeah.
All right, here's a little different one. This is an empirical one because it's based on data. It is asking the probability of a college student cheating on an exam. And this is another good example. This survey had 2 outcomes, but the results were not 50-50. And here again, that's because people are not random events. Some people are more willing to cheat than others.
Mr. Ritchie,
Yes.
what was number 13? I'm sorry.
It was 1/4.
Okay, thank you.
Okay. Yeah, 1/4. All right. So this is, they're asking you if one college student is selected at random, according to this survey, find the probability the student has cheated on an exam. So you want to prove probability of someone that has cheated on an exam. And that's going to be the number of total students who in the survey who cheated, because that satisfies the condition, and then total number of students overall. So I'll give you a minute. This one takes a little bit of another extra step. Well, I'll do the easy part. The number that cheated, because that's given to us, 850. What about the denominator?
Would it be 2,630?
Where'd you get that?
I added the 850 and the 1780.
Right. So this one didn't give us directly the total number in the sample space. They gave us the number that cheated and the number that didn't cheat. So to find the total number in the sample space, you have to add them together. And what did they come out to, Lexi?
Well, when I did it, it wasn't, I just got a percentage.
I got you just asking for the bottom number?
Yeah, right now, just the bottom number.
You got
Oh.
2,630, right?
Yeah.
Yeah.
Okay. Now that has to be reduced to get to one of these fractions. And sometimes it's easier to put it in a calculator and then find one of the answers that you put in a
Yeah, I
calculator.
can.
It's not going to be this one because that's greater than one. It's not going to be that one because that's greater than one too. So it's one of these other two. What was the percentage you got when you, or the decimal you got when you took 850 and divided it by 2630?
Let me do it again.
Okay, sorry.
No, you're fine. I got 0.323. But I can find it.
Try this one. This
It
one.
matches the last one. Yeah.
Oh, good. That's what I was going to say. That
Sorry,
one was
I didn't
close.
even notice you checked it. Sorry.
I didn't check. I was checking it right when you said it. I thought that one looked more likely. Good job.
Yes.
So this one is, if you reduce this big fraction, it would reduce down to this, which I guess we could have done that by just getting rid of we could have done that and been done with it. But I made it into something bigger than it needed to be. But anyway, the process is the important thing. Okay.
Oh, and that is correct. I didn't tell
Okay.
you, but I did read. I got the greatest common factor, so that's correct.
Okay, good. Ah, here's a good one. Notice it says majored in English or math. Sounds like an addition rule problem to me. So they're asking you, what's the probability according to this data we have? And nobody gets 2 degrees in this data. They only get one. English or math. So since nobody gets 2 degrees, we can say that these are mutually exclusive events. That might we know. Then I'll let you go from there, see what you get.
Would it be, I don't know if I did it correctly, but would it be the 0.474?
We'll
I
find
got
out.
the same thing.
Okay.
But I didn't, but when I got it, I just got 0.4.
I mean, I got it and it rounded up to 0.47. It was like 0.4739, yada, yada, yada.
Okay.
Did you do it on your phone's calculator?
Yeah. I have like a scientific calculator at home, but it's not working. So I use my
I used my
iPhone
phone
calculator.
I did too. Wait, you did the 2 divided by 5?
I added them all up, got the total, and then I added the math and English, got the total, divided them, and I got that decimal.
Somehow I did not get that. I just got the 0.4, but I guess it still counts. So.
Well, let's go through the process and see. Well, if you got 0.4739, then that would
Yes.
round to 474.
Yeah.
What
But it
was
was
the
kind of fast, so we can go ahead.
what's the numerator?
It was like 4. Hold on, I gotta do it again. I don't remember.
Wait,
Well, just tell me how did you
wouldn't-
get it?
Wouldn't
I
the
just
numerator
added-
be 1?
Oh, I added them.
No, you're
Did I do that wrong?
right. The numerator is all the students that satisfy the condition of either, well, let me do it. Let me not jump
Because I
ahead.
got 436 from the
Oh,
27
wait.
to
Oh my
11.
gosh. I didn't write the students. I just did like the number of classes. So I did there's 1. Okay, oops, that was my bad.
So the addition rule tells us that if we want to know the probability of English or math, we do the probability of English plus the probability of math. Now we know that they're mutually exclusive, so we don't have to worry about subtracting any back out. So how many people got an English degree?
209.
Out of how many total students in the survey? We had to add that up. They didn't give us that.
I should have wrote everything down. I was just kind of doing it. in
That's
the
all
head.
right. You got something. You got one of the answers. It's probably right.
920. Unless if I did that wrong, I can do it again.
No, it was 920.
Okay.
920.
See, when I did it, I didn't do the number of students. I just did the classes. I did like there's 5 classes and there's 1 English, 1 math. That's why I got the 0.4 because I didn't look at the number of students.
That's okay. Here we go. How many math majors were there?
227.
Yeah, 227.
Out of how many total students?
For 920.
All right, so we already have a common denominator. That makes adding these kind of easy. That's the same. And when we add 209 to 227, we get 436.
Yeah.
I think that's what it was.
Okay, yeah,
And-
it's a 0.474.
There we go.
Great.
Nice.
Yay.
Good job, Anna.
Thank you.
I'll let everybody get that down. Excuse me. All right. Here's another one you can do. I gotta step away from my computer for 1 second. I'll be right back. All right. Probability having blood type A positive. Here's another example of things that are not random events. For whatever reason, our blood types happen at different rates. Some are more common than others. You would think that something like that may be random, but it's not.
Do you want us to tell you what we got?
I would like you to tell me the numerator.
Okay, the numerator would be 34 and the denominator would be 100.
Okay, so here is the numerator. There were 34 people with A positive blood type. And they actually told us we didn't even have to add these up. They told us there was 100 people. And so as a decimal, that one's pretty easy to do because it's over 100, right?
Yeah.
There we go. That's another empirical probability, a case where we're using data to determine probability. All right. This one's set up a little funny, kind of a funny looking little table, but it's a man or a non-smoker. So when we see that or, we think addition rule. Probability of being a man or a non-smoker. Now let me ask you this, whenever we do an addition rule, we have to check to see whether if they're mutually exclusive events. Is it possible for a man to be a non-smoker? So is it possible for one individual to satisfy both those conditions?
Yes.
Right. So you're going to have to do first the probability of being a man in this survey anyway, plus the probability of being a non-smoker. And then you're going to have a lot of duplication in there. So you have to subtract out the probability of both of those things happening at the same time. The male non-smokers. So that gives you a little start on this. All right, in this survey, well, let me ask you this. How many total people are in this survey?
832.
I'm not sure that that's right.
Oh, wait, did I do that wrong?
Where do you find the total number of people in the survey?
It says total and then. Oh, I'm sorry. I didn't. Oops, I accidentally counted the total. It's 416.
Right, it's right here. Well, it's kind of laid out weird.
I'm sorry. I should have read that.
That's
That
okay.
makes sense. I was like, I was gonna redo my my answer because I was like, I don't see my answer there.
So when we're doing this problem, we know the total people in the sample space is always going to be 416. So don't get confused and start thinking the sample space is just men and all that kind of stuff. Is not. It's the total people in the survey. So the first one is the probability of being a man. Out of the 416 people, how many were men?
135.
Just don't think too deep into this.
Oh, how many were a man?
Right. Just how many?
200.
Right. We're not asking about smoking or anything. So there's 200 men. So the probability of being a man in this survey, 200 out of 416. Now, let's see, what is the total number of non-smokers? Not asking if they're men or women, total number of non-smokers.
322. Oh,
135.
wait. Are we still just talking about men?
No, it's just.
Oh.
Don't read anything extra into this.
Is it
All you're
322?
It's 322.
Yeah.
Okay.
This formula will take care of itself. Don't think too deeply into it. All this is saying is the probability of being a non-smoker. And there's 322 non-smokers in the survey.
Wow. I'm glad you caught that.
Now, obviously, there was a lot of overlap. We counted all the men and all the non-smokers, which means we double counted the male non-smokers. So now it's time to subtract those back out. How many, looking on this chart of data, how many male non-smokers are they?
135.
There you go. And the formula takes care of all that other stuff. You just answer the little questions one at a time. Here are the people. So we counted this 135 people. We counted them in the man group, and then we counted them again in the non-smoker group. And that's why we had to subtract it back out. So if somebody will crunch those numbers for me, that would be great.
It's 122. Wait, from the
No, it's not 122.
Oh,
200,
oh. 200 minus 135. Is that what you're saying?
no, 200
Oh, no, I'm sorry. I'm sorry.
plus 322 minus 135.
Wow, I had a brain fart. It's 387.
It's the numbers. Like that's what's throwing me off too.
I know.
So it's 387. And when you
Yeah.
divide 387 by 416, what do you get?
0.030.
That doesn't sound right at all.
Wait, you got what?
0.930. But that's a.
Oh, 930. Okay. I just heard the 30.
That's what I thought you
Oh,
said.
did I say 30? Oh, I meant 930. I'm sorry.
There we go.
I was like, wait, but that's a.
So the probability of selecting somebody at random and that being a male or a non-smoker. So it could be females too, because there's non-smokers that are female. Is 0.930. And now we've done all the practice questions and the addition rule. So Monday, excuse me, we'll get back together. I'll show you the multiplication rule and we'll do a bunch of work with that. So you all have a good weekend and I will see you. Thanks for coming today again. And I will see you on Monday.
Thank you. Good luck at your
Have a
appointment.
good appointment.
Thank you very much.
You're
Thank you.
welcome.
Christy.
Bye.
Good luck, Mr. Ritchie. Bye.
Thank you. Bye.